10 years of Redox OS and Rust. Who knows what Redox OS is? Wow, that's way more hands than I was expecting. Is this thing on? OK. So who am I? I'm Jeremy Solar. I am the creator of Redox OS. I created it in 2015. I also work at System 76 since 2017. Where I work on the Cosmic Desktop environment, the Pop! OS Linux distribution, and embedded software and electrical development. Redox OS, as you do know, is a general-purpose Unix-like microkernel written in Rust. We have tried to create from the ground up every component crafted in Rust and as much as possible in safe Rust. So the kernel is written in Rust. The drivers are written in Rust. The file system is written in Rust. The graphics stack is written in Rust. The user applications are all written in Rust. Redox OS came from a long time ago, 10 years. I was 23 years old, and I was working on computer vision. I was using C++ and OpenCV, and we were doing autonomous firearm detection in security cameras. In that kind of scenario, performance is incredibly important, especially multi-threaded applications sharing extremely large amounts of data with GPUs and also over the network. C++ has, as you probably know, a lot of pitfalls when you're dealing with that kind of scenario. And a friend of mine who is very interested in programming languages was giving me hints about things like Haskell. I saw Haskell, I'm like, that's amazing, but I'm not smart enough for that. And he sent me a link to the Rust website. It was still in the pre-stable phase. And I took a look, and the syntax was, to be honest, jarring. Coming from C++, that's kind of a crazy thing to say when you look at the syntax of C++ from a outsider perspective. But I did stumble upon one thing that really caught my attention, the mutex type in Rust. Because this is one fundamental type that I had tried to craft in C++, and it took me days of going through GDB and checking, why is this thing not working, and looking at every single thread's backtrace to figure out why. I mean, we have RAII in C++. Why am I not able to put a shared pointer and a mutex together and only give out references to that object the shared pointer holds if the mutex is locked? Rust had already solved that problem, because the thing that I had not understood at the time was the borrow checker and the fact that those references could escape. Even with RAII, there are so many ways to transform a reference to an object into other pointers that escape that scope. So at the time, I was working on a hobby OS written entirely in my first language, which is x86 assembler. That was a great first language. My second language was Visual Basic 6. I don't know if you know anything about those two languages, but they are totally polar opposites. And the reason why I was interested in x86 assembly is I was trying to write DOS applications. And I started working on an operating system that I called SolarOS. I had heard of Linux at the time, and so I thought, well, why not just throw some ego into it and just call it SolarOS? And it was really a hobby project that had no value at all. But I saw Rust, and then the pieces started to come together. The thing that really got me in was, unlike C++, the no standard mode, I could actually compile Rust for bare metal. I could compile it for any environment I wanted to compile it for without relying on an operating system. So I thought, why don't I just take my operating system and rewrite it in Rust? And that's what I did. On April 20th, 2015, I committed the very first commit of Redox OS. And it booted, and it had a GUI. It all ran inside the kernel. I don't even think you can call it a monolithic kernel at that point. It was I own everything inside the kernel. It's not even a unikernel. There wasn't even an API. It was more like a demo from the demo scene. I worked on it as kind of a fun place to try Rust things, because I could not bring it back to the C++ world at that time. And And it grew and grew until a few months later, someone posted it on Reddit. And the reason I knew is I had a public GitHub repository, and all of a sudden, the traffic spiked. And how is this possible? Why would anybody be interested in this? And then I started getting issues coming in. I don't know where they came from. They said, hey, are you serious about this? I'm like, should I be? Should I be serious about this? I went back, I traced it all back to the Reddit thread, which was done by someone named Tiki, who was a very early contributor to Redox, and saw a bunch of people who were interested in the same thing. Let's take the memory safety of Rust, and let's oxidize the lower levels of the stack. And that is actually why I named it Redox. I understand the reason why we call the language Rust is because of the fungus, but we still use the terminology of oxidizing. So redox, reduction, oxidation. It also kind of rhymes with Unix and Linux. Early 2016 is around when we started, or I started, along with Tiki as pretty much the only contributor, rewriting a whole thing to see how would we make it serious. And so that's where the microkernel came into it. And there are debates raging over the history of computer science, right? Whether microkernels are a good idea or not. I don't think writing software in general is a good idea. I mean, look where we are now. But microkernels were really interesting to me. One primary reason they're interesting is just the ability to write drivers in Rust with the standard library. So it's not like Rust on Linux, where you are writing in a custom no standard environment. You actually have a standard library, and everything is available there. You have all of the FS modules. You have threading available. You have async available. All of it is available inside of device driver, and you can write your file system using async. So we had that vision and started building it up. But we needed a way for these microkernel processes to communicate with each other without requiring all of the user space to change. One other thing that I've realized is that we will never get anywhere if we require everyone to rewrite their code for Redox. So that's what we've been working on, is trying to make Redox. Where is it now? We've been trying to make it a production-ready operating system. And a big part of that is Relibc. Relibc provides the POSIX-compatible API for Redox. It has Linux and Redox backends. But at the very top level for applications, it generates header files with cbindgen, and all of the implementations use as much safe as possible and are abstracted from the platform. So we can have a Linux backend, a Redox backend, a BSD backend. The Redox backend can use special things, which I'll talk about later, to adapt to the microkernel architecture underneath. We've implemented namespaces for capability-based security. So this allows for really tight allocation of resources. In a microkernel, that's critical. We run most of the drivers in a special namespace called the null namespace, where they have no ability to open new files. Now, I don't know who knows about Cloud ABI or WASI, but these are also capability-based systems that try to model the same thing. You are given the resources you're allowed to use, and then you cannot acquire new resources later. So you have a configurable method to lock down the available resources for a process. We've improved hardware support greatly. At the very beginning, the only supported target was 32-bit x86. At the time, this was, you can remind me, it was 2015. Where was 32-bit x86 at that time? It was dead. It was completely dead. Every single manufacturer had given up on it. The last vestige of it was the Atom processors from Intel, and they had wiped it out. They had switched it over to 64-bit. So I took on a very big project to rewrite the Redox kernel for 64-bit support. Now we support 64-bit and 32-bit x86. I added it back in like as just a fun project. I got to bring back 32-bit support. Redox will run on a Pentium 2. We have ARM 64 support, and we have RISC-V 64-bit support. We have a USB 3 host controller driver that works on all of those architectures. So that provides us with input and other devices on all of those architectures. We have ACPI support that's building, and that is thanks to the Rust OS dev project, which is also where the monthly blog post comes from about Rust OS dev. And Isaac Woods is a big contributor. And we have really gotten into trying to implement Linux APIs and POSIX APIs so that programs coming from Linux are source compatible with Redox. So that means you have code that uses special APIs, things like epoll, IOU ring. We've actually implemented epoll and IOU ring on Redox. And lastly, but not least, my favorite point on this slide is the Cosmic Desktop. It is kind of a life hack to be able to turn your job into your hobby. And my job recently has involved about 90% of my time being spent writing applications for the Cosmic Desktop. The Cosmic Desktop also, from the compositor upwards through the toolkit, through the applications, is all written in Rust. Because of Winit and other projects like SoftBuffer and WGPU, we have been able to port most of those applications over to Redox. I have a little secret surprise for you later, where I'll reveal that we're running a little more on Redox than you may imagine. This is a screenshot of Redox running Doom, which is, I'm a big retro gamer. I have a Pentium 2 with a Sound Blaster 16, and it runs Doom natively. But running it inside of Redox is pretty cool. It has some Cosmic applications like the file manager, the editor, and the terminal. And inside the terminal, you'll notice that new shell is running. We ported new shell to Redox, which was actually really simple because all of the underlying support for POSIX APIs was there. The architecture was actually finalized way back in the early days. I walked back and forth talking to myself like a maniac, exactly like I'm doing right now. And I had debates with myself about how would we connect the disk driver and the file system driver. I read through the Plan 9 system calls, the Minix system calls. Plan 9 is not a microkernel, but they have this idea of having every kind of device have its own file system. And Minix 3 was probably the most advanced microkernel at the time. They were running X11 and window managers and all kinds of stuff. So I combined those two ideas into a really simple system call interface that uses a file API for communications between drivers. The kernel itself is less than 30,000 lines of code. A lot of that is stuff we haven't condensed down for architecture-specific support. So when I say 30,000 lines, I would say the realistic endpoint of that is about 10,000 lines of code. 100,000 lines with dependencies, but realize a lot of those dependencies are not being fully used. Like we have, for example, we're counting in that count the Rust core library. Services and drivers are running in separate user space programs. And this is how that looks. For example, if an application wants to open a file, it makes a system call to open the file, going through Relibc. And the kernel gets it, and it uses the namespace support in the kernel to decide which version of a scheme implementation gets to handle that call. So in this way, you can have OS-level virtualization, because you can have multiple file system handlers all servicing the same scheme. You can put an application inside of a chroot, for example, by just implementing the file scheme and changing the files that the application gets access to. Then Redox FS will have to call to NVMED. Now, the disks from the NVMe driver are just files. They're just files, just like on Linux. We have a concept for how we want to stabilize the API and the ABI. So this is something that's always difficult when you haven't finally finished a product, when you're still working on, and you know there's so many questions you haven't answered yet. How are you going to keep adding new things without breaking the old things? And dynamic linking really is part of the answer. Unfortunately, it is a difficult thing to do with Rust. But with the architecture of Redox and most things going through the file system API, we're actually able to make dynamically linked binaries be forward compatible. So they will run on future versions of Redox, even if the system call APIs change. We don't actually expose the system calls to user space applications. The benefit of that is when we go for more advanced and more performant ways of communicating between services, which I will talk about later, those ways are not burdened by trying to update all of the past applications. They don't have to be updated. They may end up having a new API that will access those more directly, but we will maintain future compatibility. Relibc is a huge part of Redox. I would say it is the largest singular project that we work on. It's a C library that's written in Rust. It uses no standard. It uses C bindgen to generate headers. It tries to use as little unsafe as possible. So for example, the printf implementation, it takes in the unsafe pointers from the C program, and then it cleans them all up into safe stuff that it can pass through to something that actually formats and prints. So yes, there is a point in time when printf could get something invalid, but that point in time is not inside of the formatting code. So segmenting those out and knowing where the boundaries are really helps. And we've been able to reduce the unsafe in Relibc vastly over the past few years. So the backends are a little different. For Linux, system calls go directly through Relibc to the system call API. For Redox, a lot of system calls are implemented in user space. We have an asynchronous atomic method of setting signal masks, for example. This would go through the Linux kernel through a system call. On Redox, it changes a shared memory address atomically. By doing it that way, we have removed a system call. So these are the kind of benefits you can have when you can modify the system calls without breaking user space. This is just an example of how Redox is easy to change. Redox is actually a declarative operating system. Every install of Redox is defined by a TOML file, just like Cargo. Just like Cargo has a TOML file. We're working on a lock file format as well, so we could lock down versions of packages. So imagine being able to produce your operating system the same way you produce your Rust project. And there's other stuff on this slide, but I think I'm going to go forward, because we need to see the demo. Redox mission statement. Yeah, we will provide a more secure and reliable alternative to Linux and BSD in cloud, edge, and desktop use cases. I think if we keep working on it, we'll be able to. So where might this be useful? I have really gotten into the idea of being a container host. And the reason is the hardware variability is much less than in the desktop world. You can really target very specific hardware. And you can utilize Rust's capabilities as well as microkernel capabilities to get the best possible container host. So for example, capability-based namespaces in Redox allow OS-level virtualization, which has no overhead whatsoever. Applications that run in OS-level containers do not have any virtualization overhead. We could run WASI microservices natively. We could create reproducible environments using our declarative configuration, as I mentioned before. And I haven't gotten to this point yet, but when we start doing display drivers, I believe that we could allow easier access for multiple guests to access physical hardware with less overhead. As a safe runtime for cloud applications, so there is kind of two drastic extremes to how people deploy cloud applications. There's things like Amazon's Lambda platform, which uses a very small VM to launch very specialized code. And then there's things like taking the entire Ubuntu server image and dumping in your one application on top of it. But there has to be something in between. Imagine if you could tailor your operating system easily to the application. Imagine if you could create the security environment you need by just editing a TOML file. And my favorite place for Redox, regardless of how insane it would be to actually approach it, is desktop Redox. We've adopted freedesktop.org standards as much as possible. We're working on Wayland support. A lot of Wayland support issues needed work in Relibc for us to implement insane Unix socket communication methods. Cosmic also, it provides us with a test case. Like we can test a very modular set of desktop applications and applets and the panel They're all individual processes in Cosmic. That allows us to compose things at our own pace. We can containerize the desktop as well. I haven't gone very much into this thinking about it, but exposing those containerization and capability-based security implementations to applications could be very advantageous for things like web browsers or implementing things like Flatpak. There are significant challenges. A big thing that comes up all the time is performance. We always try to do things right at first, and right does not always mean optimized. If it compiles, if it runs, if it tests, that doesn't mean it's fast. So going back and making things fast is a very big part of our future. And we have some ideas about how to change the architecture of Redox without breaking applications to make things vastly faster. So the Ring Buffers project is funded by IntelNet. And what that will allow us is for drivers that have to communicate between each other, like the network driver and the network stack, or the file system and the disk driver, they'll be able to communicate in an asynchronous ring buffer just using shared memory. And the only time they'd have to go out to the kernel is to handle contention or to handle waking up the other process. Compute acceleration, I'm confident that we can get to the level of Linux because I've looked through the Linux APIs deeply while developing Cosmic, and I do not believe that our architecture restricts us from improving performance there. Then we have scheduler improvements, which we're going to apply to the entire stack. They will have benefits everywhere. So things like directly switching to the services or drivers that are handling a system call. Or implementing EEVDF, which is a Linux kernel scheduler that has a really long name that makes sense when you go through it very slowly. So there are lots of things that we can do with context switching as well to reduce the times. We actually have faster context switches than Linux in some cases, but we think we can get better by reducing the number of context switches to allow drivers to run on different CPUs and share things through shared memory, so context switches aren't even needed. And of course, this is an active research area, and there are a lot of smart people here. There are a lot of people who are way smarter than me here. And I constantly learn new things. Earlier, I learned about enums during one of the community talks. And now I have to go back and rewrite a whole bunch of stuff in Relibc. Hardware compatibility is hard. Hardware is insane. The people who work in that world are very deadline focused. And if they produce documentation, it is not for the driver developers, because the driver developers often are developing it with direct contact with the people who make the firmware and the electrical design. So for Redox, documentation on the hardware is very important, but a lot of it is missing. There is no documentation for AMD GPUs or NVIDIA GPUs. For AMD GPUs, all the documentation is in the Linux kernel. Intel is the only GPU vendor that actually provides full documentation, but it's about 10,000 pages. So if you want to go off and do that project, that would be great. So for us to achieve some of our use cases, we have to partner with hardware vendors, and we have to convince them that they should be writing drivers for Redox, or we have to be able to port drivers over from Linux and run them in some kind of virtualized form on Redox. For desktop Redox, it becomes an even harder problem, because there are so many vendors that already don't care about Linux. Why would they care about Redox? So yeah. Completeness is another problem. We are completely a community-developed project. And when you have people that are driven only by their own desires to write software instead of by being paid to write software, they will do what they want to do, and then they'll disappear. And I have been guilty of this too. Sometimes I have things that pull me away from Redox. The way that we can solve this problem is by going back to things that are already written and trying to implement testing around it. We've brought in compliance tests for our C library, OpenPOSIX test suite. There's OS test suite from Sortix, which was funded by NGI Zero, which also funds Redox projects. And yeah, the GUI also needs some work. GPU acceleration support is a big one I want to start working on soon. We're going to be porting Wayland. And then accessibility is one that we're also working on in Cosmic. And formal verification is something we've been using in more places. Redox FS has formal verification on its permissions model. But extending it to other parts of Redox FS ended up being more difficult than I would have liked. Safety is a big thing for Redox, so we're very serious about capability-based security, and we want to investigate formal proofs. We believe that Rust is providing us with advantages, but we want academics and security researchers and third parties to actually be involved in testing Redox. Our community, our last release was a while ago. I'm probably going to do one right after RustConf. You guys are keeping me from doing one. There's a dozen significant contributors for the latest release. We have 1,000 people on our Matrix chat. We also bridge it over to Discord if you prefer that. We have a nonprofit that is managed by a 4-person board of directors, a full-time community manager, a part-time build engineer who was just hired, and we have 3 students that are working on grants from NGI Zero Commons and NLNet. We are hiring, if you're interested in a full-time developer job and you're interested in working on what I would love to work on, if I wasn't also loving to work on Cosmic as well, then you can send an email to us. So I have to give a shout out to NGI Zero. They funded a number of projects over the past few years. They give us grants to pay people directly for these projects. So the nonprofit doesn't handle the funds. We handle the selecting people and helping them through their proposals and then getting them grants. And those grants have brought us incredible things. Process management was moved to user space. So this is Unix-style process management. Signals as well, so Unix-style signals. We have some capabilities work to improve our capability-based security. And then the ring buffer project that I talked about is another proposal we have with them to try and improve performance between services and drivers. So, and all of those changes did not require changes to the whole stack. They just, there was only one change recently that required a lot of changes throughout the whole stack, and that was enabling dynamic linking so we could actually have the stable ABI. Now that we have that all sorted, we are landing these changes without having to make changes to every single application or recompiling them. So if you would like to be involved, well, come find me after this talk. I would love to have your company fund Redox. I'd love to have you be involved in contributing to Redox. Mostly, we need hardware vendors to actually care about getting us documentation or getting us developer time to create drivers. A lot of our projects are also community funded. We hope that by 2027, we will have Redox in some real-world usage. And you can reach out to us if you're interested in sponsoring. So let's take a look at Redox OS. I don't have very much time, but I don't need to, because the secret is I have already been doing the live demo. I've been doing my presentation inside of Redox. So here we have a POSIX-compliant command line. We use uutils, which I'm sure many of you are aware of, for our core utils. And we also have screen fetch, things like that. Cosmic applications are fully supported, so all of the settings work correctly. For example, you can switch dark and light mode, maybe, who knows? Maybe not. I'm not gonna mess with that during a demo. We have games, we have Doom. We have a lot more games that I can't show you because they require proprietary assets. But yeah, performance is actually quite good for a hobby OS, and now we're trying to level it up. How can we get it to the place where we can consider putting this in the real world and actually using it? And I'm going to stop there, and I hope you will come and visit me later. It's been so great having talks with so many of you over the past day and a half, and I hope to have some more. So thank you.